Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's Design News webinar. Automotive, will autonomous cars be electric? Sponsored by Highland Molex, IPEX, Protolabs, and Siemens, and broadcast by Informa. I'm Chris Keach, and I'll be your moderator today. We have just a few brief announcements before we begin. This webinar is designed to be interactive. The dock of widgets at the bottom of your screen will allow you to learn about today's speakers, download resources, share this webinar via social media outlets, and participate in our Q&A session that takes place at the end of our presentation. The slides will advance automatically throughout the event, and you may also download a copy of the slides via the resources widget. Towards the end of our webinar, we will ask you to complete our survey found on the right-hand side of your screen. Please take a moment to fill this out before leaving us today, as your feedback will provide us with valuable information on how we can improve future events. And lastly, if you're experiencing any technical problems, please click on the Help widget found at the bottom of your screen or type your issue into the Q&A text area, and we will be glad to offer one-on-one assistance. And now on to the presentation. Automotive, will autonomous cars be electric? Discussing today's topic is Sam Abu Al-Samid, Principal Analyst, Navigant Research's Mobility Research Service. To learn more about our speaker, please visit the Bios widget. It's with great pleasure I now turn this special session over to Sam to begin. Sam, take it away.
Thank you very much, Chris. And let's move over. Okay, so just before I answer the question in the title of this webinar, let's set the stage a little bit with where transportation is today and where we think it's going, or at least where we at Navigant Research think it's going over the next 15 to 20 years. Navigant Research is the market research arm of Navigant Consulting's energy practice, and part of what we do, particularly in the transportation area, is looking at the market for a variety of different transportation-related technologies that are related to energy use. And so we, among other things, we forecast overall light-duty vehicle sales and sales of a market reach of a wide variety of technologies, including automated driving. Our most recent light-duty vehicle sales forecast takes us through 2030, and we're currently projecting a continued increase in overall vehicle sales every year, growing about 4% annually, till we get to about 138 million by 2030. Which means that we're going to have a continuing increase in the vehicle population, because the vehicles we're building today tend to be more durable and last longer than ever before. Current average age of vehicles in the U.S. is almost 12 years now. And as we build vehicles better and build more of them, even as sales will tend to plateau, as we expect them to here in North America and largely in Europe, and eventually start to decline somewhat, we're still going to see an overall increase in demand from other regions and an increase in the overall vehicle population, which is in turn going to lead to a variety of societal issues that we're already seeing and that are likely to only get worse unless we make some changes. And so that's one of the big drivers for the move towards autonomous vehicles, is to start getting the drivers, the human drivers, out of the vehicle so we can better manage traffic flow, improve safety, and make mobility, personal mobility, accessible to more people, especially as the world gets more and more urbanized. So our current light-duty vehicle forecast for light-duty automated vehicles goes through 2035, and what we're looking at here in this chart is a breakdown by different levels of automation. And this is based on the SAE definitions in SAE J3016, which is a 6-level grade from level 0, which is no automation at all, up through level 5, which is vehicles that are capable of operating without human intervention under any and all conditions. And in between that, we have, from level 2 at partial automation, where the human driver still has to maintain, is still responsible and has to pay attention and watch the road and be ready to take control, to level 3, where you've got conditional automation, where the vehicle is capable of operating without human supervision under very certain specific conditions. Level 4, getting us into where vehicles are able to operate without human intervention or human supervision under a very specified operating domain. and then level 5, which is, it expands that to the operating domain to any and all conditions. And so our forecast for that, we're starting to see, an increasing number of vehicles that are capable of level 2 automation, and that includes systems on the road today like Tesla Autopilot, General Motors Super Cruise system, Volvo Pilot Assist. These are systems that, were, in some cases like Super Cruise, they're hands-off systems, but the driver still has to pay attention to the road. And we expect that to be the largest, grow to be the largest segment of the market by the mid-2020s. But as we get into the early 2020s, we're also going to start to see more of these so-called level 3 systems. And the first production level 3 system that was announced, but is not yet actually in production, is Audi's Traffic Jam Pilot, which is capable of allowing the driver to go eyes off the road at speeds up to about 37 miles an hour. That hasn't yet been homologated and approved by regulators in Europe or anywhere else yet, so it's still not actually available for sale, but that system has been announced. Level 4 systems are the types of systems we see from companies like Waymo, Aptiv, GM Cruise, and many others that don't require any human intervention anymore. And if something goes wrong, the human doesn't have to take over, but the system can get itself to a minimum risk condition. And we expect that to start growing slowly over the next several years with some limited deployments in cities where both the traffic conditions and the weather conditions and infrastructure capabilities enable it to be used safely. But in the early 20s, we're still looking at only volumes in the tens to hundreds of thousands of vehicles globally, and finally growing to some significant volumes in the millions, in about the 5 million range by the middle part of the next decade, and then growing more beyond that. What we don't expect to see any significant volumes of until at least towards the end of the decade is level 5. And in this chart here, combined level 4 and 5 together, that's what level 4 plus is. It's the combination of 4 and 5. Those we don't expect to see. Level 5 we don't expect to see really deployed before towards the end of the decade. The challenges that developers are finding with getting these vehicles to operate safely beyond limited conditions are proving extremely onerous. And so exactly when they'll start to solve some of those problems is not really clear yet at this point. So here we've got level 4 and 5 deployments broken down by region. And based on North America, Eastern and Western Europe, Asia Pacific, and as you can see, Asia Pacific is really, we expect it to be by far and away the largest market for L4 deployments, and particularly in China. China has a unique combination of a government that has the ability to push things in certain directions more so than many other countries do, and the challenges of extreme congestion and air quality problems in many of their major cities. And so there's a big push from the Chinese regulators to get both electrified vehicles and automation on the road in order to address some of these societal problems that they have. Overall, by the mid-2030s, we expect to see somewhere in the neighborhood of 34, 35 million overall highly automated vehicles deployed globally. And I use the word deployed here very explicitly because what we don't expect is most of these vehicles to ever be sold to consumers. The vast majority of these vehicles, except for some applications at the very high end of the market, will probably only ever be available through mobility services. And I'll get into more why that is in a moment. So one of the things that comes with adding driving automation to vehicles is it dramatically increases the electrical complexity of the vehicle. You have greater electrical demand because you have all these sensors. This is an example of the GM Cruise Chevy Bolt, automated Bolt that's being tested in San Francisco, and they have a fleet of about 180 of these in San Francisco and more in other areas in Michigan and other regions where they're testing. And this is a prime example. This vehicle has 40 sensors on it that are dedicated to the automated driving task. You've got 5 LiDAR sensors, 14 cameras, and 21 radar sensors, and short, medium, and long-range sensors. In fact, also some ultra-short-range sensors. And all of these sensors require connections in order to transmit the data to the computer that's doing the processing, but also to get power. These sensors, especially LiDAR, but also camera and radar, draw a lot of power, electrical power. And this is one of the things that we expect to be drivers for electrification in these types of vehicles going forward. What you see here is the wiring harnesses for the current production Chevrolet Bolt on the left, and then the version for the automated Bolt on the right. And as you can see, there's vastly more complexity here, wires and connectors to tap into all these sensors and transmit the data around. And you're talking terabytes of data an hour that may be captured in some of these vehicles. And you also have multiple computers. You have redundant power supplies in order to, because one of the things that changes as we go from human-driven vehicles to automated vehicles is you need a degree of redundancy that we've never had in vehicles before. In the past, today with driver assistance systems like adaptive cruise control or lane keeping, or even more basic systems like power steering or power brakes. In all of those cases, if something goes wrong with one of those systems, whether it's in the sensing, the compute, or the actuation, the human that's driving the vehicle is expected to be the backup system. So if your power brake booster fails, you can still stop the vehicle. The human can still stop the vehicle by just pressing harder on the brake pedal. If your electric power steering fails, you can still control the direction of the vehicle. You might have to put some more torque into the steering wheel to move it, but you can still do that. The human out of that driving loop, and whether or not you have human controls in the vehicle, you now have to have backup systems for all this to enable the vehicle to stop, accelerate, steer without a human taking over. Because in many cases, these vehicles may not even be carrying a human that is there to take over. So that adds to the complexity of this, and that means you also need things like redundant steering actuators, redundant brake actuation, as well as all the different sensor modalities. So I mentioned, that we expect that the vast majority of automated vehicles going forward are going to be deployed in mobility services, and so that means a real change in the business model around these vehicles. And there's a number of reasons for that. Because of the complexity of these vehicles, there's going to be significantly increased costs for the technology up front. But one of the things that we've already started to see change in the market, starting with Tesla. Tesla debuted over-the-air updates several years ago with the Model S for safety-critical systems. Many manufacturers have been doing OTA updates for a while on telematics and connectivity systems. But Tesla was the first to deploy it for safety-critical systems. And as we move into the world of automation, we're going to need to do that, for all of these vehicles. They're going to require updates. They're also going to require updates to maps, updates for cybersecurity, because the last thing you want is malicious hackers breaking in and doing something bad with a fleet of automated vehicles. But those updates, the current model that we've had for 130 years in the auto industry is a manufacturer designs, builds, sells a vehicle to a consumer, and then moves on, and they work on the next generation of the vehicle. You don't do continuing updates on a vehicle that's in use in the field. But that changes with automation, because now this is still a very mature technology, and it's evolving, and both for functional and safety reasons, but also the aforementioned security reasons. You're going to have to do these updates on these vehicles on a regular basis, and there's a significant cost associated with developing, validating, and to a lesser degree distributing those updates. So with affordability already being a problem with the vehicles we have today, average transaction price is now up over $35,000. It's only going to get worse when you add all this additional technology on there. You've got 3 main options for how you pay for this lifetime support of the vehicle. One is to build it into the bill of materials and, again, increase the price of the car, or you can require the customer to pay for a subscription to get updates over the life of the vehicle, and customers aren't going to like that either. Or you deploy it through a services model, a mobility service model, where you can build that into the fare cost, the per use cost of that vehicle, and kind of hide it in there. And then the manufacturer or fleet operator now has a recurring revenue stream that can help fund that ongoing support. So that's a big part of why we see the shift towards mobility services with automated vehicles rather than selling them to individual consumers. So, electrified vehicles, at Navient, this is our forecast for electrified vehicles through 2030, and this includes both plug-in hybrids and full battery electric vehicles, as well as fuel cells, and also regular hybrids as well. We're projecting sales of those to approach about 28 million by the end of the 2020s, with the vast majority of those increasingly being battery electric. But there will also be a significant proportion of plug-in hybrids and regular hybrids. Fuel cells we expect to be a fairly small niche of light-duty vehicles, electrified light-duty vehicles, at least through the decade, but that could change depending on adoption of the automated mobility services. So if we're going to have electrified vehicles in fleet operations, now you have to have a whole infrastructure associated with that. And an example of how that's being built out is GM Cruise in San Francisco, prepping for their commercial launch, which they're at least officially still planning for sometime later this year. One of their first remote depots that they put in is in a parking garage in the Embarcadero district of the city. And last year they installed 18 DC fast chargers in there to support their vehicles. And the reason why they're using DC fast charging is if you're going to operate a fleet, now you have the problem of, in order to make it a commercially viable operation, you need to minimize your downtime. You need to have maximum utilization of these vehicles. So you can't afford to have them sitting around for 4, 5, 6 hours a day charging, or longer than that. They need to get in and get back on the road as quickly as possible, generating revenues. And the analog here is, if you think of the airline model, airlines only make money with their planes when they are in the sky, traveling from one point to another, carrying passengers and cargo. When they're sitting on the tarmac, they're not making money, they're costing you money. The same thing applies for a fleet operator, whether it's GM Cruise or Waymo or anybody else that wants to operate an autonomous mobility fleet. They need to have those vehicles available and in use as much of the day as possible. So GM, as I said, has put in a depot with DC fast chargers. They've also got a main service depot that handles most of their fleet in the city of South San Francisco on the south side of town. Again, for Ford and ARGO in Miami, they've been testing there for over a year now. And, part of what they're doing is they're looking at the use cases for their vehicles, in addition to developing the automated driving technology. And, they're looking at where the vehicle is going to be used, trying to develop the logistics platform to make sure that, they can deploy the vehicles to the right places at the right time, minimize deadheading miles, which is a real burden. If you look at current taxi fleets, the New York City taxi fleet, for example, on average has about a 50% utilization rate, which means about 12 hours of the day, a typical New York cab is actually carrying a fare-paying customer. That's not really going to be good enough to really cover the cost of all this technology. You need to have much higher utilization than that. So Ford is looking at a variety of different things. One of the choices that Ford made is for their first generation AV that's scheduled to come out in 2021. They've opted not to go with a battery electric vehicle, as GM has. They've opted to use a hybrid powertrain. Now, the vehicle that will be deployed is not going to look like the Fusions. It's not going to be a sedan like the Fusion hybrids that Ford is using today for their development purposes. It's going to be a multi-purpose vehicle specifically designed for these mobility applications, but it is going to use a hybrid powertrain, because what they have said is we don't think for these first generation of vehicles that if we're DC fast charging them all the time, that the battery durability is going to be good enough. It's going to take too much time, cost too much money, and so they're going with a hybrid that they can fuel up, get in and out quickly, and get it back on the road. But they're also looking at what are the other use cases for this vehicle. So that's why they've been testing with different body form factors like the Transit Connect and the Escape. And as part of that work, they're also looking at, okay, where do we need to have our infrastructure, our service depots, so main infrastructure, smaller outlying remote depots that can do quick cleanup if the vehicle needs to be cleaned, get it fueled, get it back on the road, and are also developing their ride-hailing app as well as other things. But a big segment of the automated mobility fleet is going to be low-speed autonomous shuttles. And we've already got some of these on the road in a variety of places. Navia, a French company, has over 100 of their autonomous shuttles operating in various cities in Europe, North America, and Singapore. And May Mobility, based in Ann Arbor, Michigan, just launched in their 4th city last week in Providence, Rhode Island. They started in Detroit. They're in Columbus, Ohio, and Chicago. And these are all vehicles that operate only at speeds up to 25 miles an hour. Other types of vehicles we're likely to see going forward on the left is the Toyota e-Pallet concept that they unveiled at the 2018 CES, which is designed, again, specifically to be an autonomous vehicle that can provide a number of different use cases. It's designed to be built in different sizes, to carry passengers, to carry cargo, packages, food deliveries. And in the middle is the Rindspeed Snap concept, which was unveiled a couple of years ago. This is kind of a different take on the problem. Using an electric skateboard chassis and then having different pods that can snap onto it. So you have passenger pods, you have cargo pods for different use cases at different times of the day. Because one of the things what GM is launching with is a ride-hailing platform, similar to what Waymo is doing today in Chandler, and Aptiv is doing in Las Vegas with Lyft. They're all they've been focused on the ride-hailing application, but as I said, taxis don't have they don't have as much utilization as you'd like. The New York taxis with 50% utilization. Utilization for average ride-hail cars is probably even less than that. And it varies at different times of the day, and that's why we have ride-hailing companies doing surge charging. So you've got these companies that that are looking at designing vehicles, re-architecting the vehicle to be able to handle multiple use cases, so that you can easily and quickly switch from one use case to another as needed throughout the course of the day. As I said, not everyone is going fully electric. Ford has opted for the hybrid approach for their upcoming vehicle. Waymo is currently operating a fleet of 600 Chrysler Pacifica hybrids, which are actually plug-in hybrids, but they also have ordered a fleet of Jaguar I-Paces, which are battery electric vehicles. So I think what we're going to see in the coming years is a mix of electrified platforms. So to go back to the original question, are AVs going to be electric? They're going to be electrified. For depending on the use case and the timing, I think all of these vehicles will have some degree of electrification, because that electrical complexity I talked about earlier, there's a lot of power demand, and that can be anywhere from 2 to 4 kilowatts of power to drive the sensors, to drive the actuators, and to drive the computers in these vehicles. These vehicles have very powerful computers in them in order to process all this AI, to read all this data, try to process it, understand what's going on in the world around the vehicle, and then make decisions about where that vehicle should go in order to get from its starting point to the destination that's been selected for each individual trip. And so, current vehicles that have 12-volt electrical systems are generally limited to about 2 to 2.5 kilowatts of electrical power. And one of the reasons why we're seeing a number of manufacturers starting to adopt 48-volt electrical systems is in order to provide greater electrical power to meet the demands of all the features that we're increasingly putting in vehicles. And as we get into automation, putting in more and more automation, that's one of those features. We're already using most of the 2 kilowatts that's being demanded from the features we have today, like our heated seats and heated steering wheels and massaging seats and fancy audio systems and all the other goodies that we have in our cars. And so there isn't really enough margin to add a highly automated system on top of that. So that's why the push to electrify. And in addition to that, because these vehicles are primarily going to be operated in fleets, operating costs becomes a more significant factor. For an individual consumer that drives 12, 15,000 miles a year, operating cost is not insignificant, but compared to the purchase cost of the vehicle, there's a better balance there. But when you're talking about operating a fleet where your vehicles are operating 80, 100, 150, maybe 200,000 miles a year, now all of a sudden the operating cost becomes a much bigger proportion of the total cost of ownership of that vehicle. And so going to electrification can dramatically reduce the energy costs to operate that vehicle, as well as providing the energy that you need for these operations. And because of the high energy demand of these vehicles, for a battery electric vehicle like the automated Bolt, it's estimated that the AV system on that is going to reduce the range of an electric vehicle like that by up to 40%, and also perhaps reduce the durability of the batteries depending on how you handle that. And that's where we get into more of this mobility ecosystem where there's some interesting challenges with doing electrification and automation together with mobility services. GM, as I mentioned, is doing DC fast charging. Waymo will probably be doing the same thing with their fleets, at least initially, because they're based on existing vehicles. But as we start to get into next generation vehicles, because of the need for high utilization and electrification, I think we're going to start seeing more changes in the vehicle architecture that I showed before with those shuttle vehicles, where some ideas that have been considered and tried in the past that didn't really go anywhere now start to potentially have some real viability. One of those potential concepts is battery swap. We saw Better Place try and fail with battery swap in Israel earlier this decade. Tesla briefly operated a single battery swap station somewhere in the Central Valley. But the problem with those applications when you're talking about consumer-owned vehicles is there's the cost associated with doing a battery swap versus just plugging it in. And also, consumers are less likely to want to do a battery swap because they don't know the history of the battery they're getting or the condition of the battery they're getting. There's also the problem of, because every different vehicle model has a different battery pack format. If you were to try to operate a commercial battery swapping system today with the types of EVs we have on the road today, you would have to stock so many different kinds of batteries, it would not make any sense. It would never be commercially viable. But if you start thinking about it from the perspective of operating an autonomous fleet in a single city, you're more likely to have, and you can design those vehicles from scratch, you can have a consistent battery pack format. You can have a homogeneous fleet of the same type of vehicle that all use the same battery pack. And because it's a fleet that's operating them, they know the history of every one of those batteries. So if you can have a battery swap system that swaps, replaces a battery in 90 seconds, now you can take that battery out of the vehicle, put in a freshly charged battery, get that vehicle back on the road. And that also helps in another way with operating costs, because one of the issues with DC fast charging is when you've got commercial use of electricity like that, for your home energy use, for your home electricity, you generally get charged a flat rate based on just a standard metered rate based on how many kilowatt hours you use, and typically there'll be a peak and an off-peak rate, but you're just paying per kilowatt hour. But when you start talking about commercial applications, utilities have demand charges, and because if you have, if most of your electricity use is, say, 100 kilowatts. That's your average electricity use over the course of a month, at any given time. But it occasionally spikes above that. In order to prevent brownouts and provide you provide a consistent power delivery, utilities have to build up excess capacity in order to meet those brief spikes. And that costs a lot of money. And so for commercial customers, they have demand charges. When you go above a certain set power rate, then they start charging you significantly more. And that's one of the issues that I think has hurt Tesla with superchargers, why they've backed away from unlimited supercharging, is because of the cost of demand charges. And this will be an even greater cost for fleet operators of battery electric autonomous vehicles. When you've got thousands of vehicles in a city, those demand charges can add up very quickly. So if you went to a battery swap model, now you have the potential to decouple the charging from the use of the vehicle. And you could have a rack of batteries that are sitting there in your depot, all the same type of battery. They can be charged at a much slower rate, so you don't incur demand charges. But you still have the ability to minimize downtime for the vehicles that are on the road. Now that rack of batteries also can potentially serve another purpose, which is vehicle to grid. That again, as with battery swapping, because of the lack of scale and different batteries and everything, different formulas, that's always been a challenge to try to get implemented anywhere. And there's also the challenge of dealing with different systems from the 3,000 different power utilities, electrical utilities that operate across the United States. But if you're talking about operating in a geofenced area in a specific city with only one utility, and now you've got banks of batteries that are being flow charged, those same batteries could also become a grid buffer for the utility. And so now there's the opportunity for new revenue models for the fleet operators, whether they be independent fleet operators or OEMs operating their own mobility fleets. You have potential for partnerships with utilities that can utilize those batteries and potentially some revenue sharing there. Another interesting potential opportunity here is fuel cells. Again, because of the quick turnaround, fuel cell vehicle can be refueled in just a few minutes and be back on the road. And one of the issues again with consumer use of fuel cell vehicles is you need a lot of infrastructure because people are going to go anywhere they want, anytime they want, and they expect to have access to fueling infrastructure, just as they do today with gas stations and increasingly with EV charging stations. And that poses a problem. But if you're talking about a fleet that's operating, say, in a place like San Francisco, and is staying within the confines of the city limits or even the surrounding area, you could have a fleet of automated mobility vehicles operating in that area that could be serviced by just a small handful of stations. And those stations could have higher utilization because of the size of the fleet, but the vehicles could get fueled and be back on the road very quickly, just as they can with battery swap or some of the other options. So there's some interesting possibilities there with fuel cells because, again, keep in mind fuel cell vehicles are electric, even though they're generating their electricity on the fly from hydrogen. So as we get into this, we start to think about these types of vehicles because they're going to be electrified and increasingly electric entirely. And you're taking the driver out of the equation. You have the opportunity, to rethink, the interior of the vehicle. GM has already shown a version of their autonomous Bolt without a steering wheel and pedals, and they've applied for a waiver from NHTSA that would allow them to do this because right now, under federal motor vehicle safety standards, you have to have those human controls. But NHTSA is currently evaluating that waiver request, and we'll see if they approve it before GM starts to deploy their fleet in San Francisco. But there's also a lot of other new opportunities. Besides the controls, there's the interior configuration of the vehicle. You can buy, again, because you've got an electric vehicle, if you've got the battery all underneath the floor, if you don't have to have controls, you can start to do things like have the seats swivel around and create a lounge kind of environment like the Mercedes FO15 concept from a few years ago. Or something like the Volvo 360C that was shown off last fall, that can transition from a workspace to a party environment to even a sleeping environment. So having that combination of automation and electrification enables a lot more flexibility than we've had with vehicle design in the past. And for that, I will toss it back to Chris to ask some questions.
All right, thank you, Sam. Now, before we begin with today's Q&A, please direct your attention to our webinar survey available on the right-hand side of the presentation window. If you closed the survey, you can reopen the widget by clicking on the icon along the bottom of your screen. Thank you in advance for filling out the feedback form. Your participation in this survey allows us to better serve you. We're going to now move on to the question and answer portion of our event. As a reminder, to participate in our Q&A session, just type your question into the text area located to the right of the presentation window, or click on the Q&A icon at the bottom of your screen. And please note that we'll try to get to as many questions as we can in the time that we have left. If we don't get to your question today, someone will get back to you after the program is over. And so let's go ahead and get started with a few questions here for you. Looks like we have one in here that says, some of the current prototype AVs being tested by companies like Aptiv aren't electric. So why do we need to electrify for autonomy?
Yeah, so that's a good question. The fleet of vehicles that Aptiv is currently operating in Las Vegas and some other locations are based on the BMW 5 Series sedan, and you're right, they're not electric, they're not even hybrids. But in the case of those particular vehicles, what Aptiv has done, and some other companies developing similar technologies have done, is because of they know the use case, they've gone in and put in extra heavy-duty alternators. They've beefed up the stock electrical system in there in order to provide the electrical power demands of the system, and at the same time they can also disable some of the features that might be drawing on the electrical system of the vehicle, and allow it to be used for more reliably for automated driving. When they get to actual larger scale commercial deployments, their plan is to shift to an electric vehicle of some sort. They haven't said yet what that's going to be, but they do want to deploy their on a fully an electrified vehicle at least. And that's why most of the if you look at most of the companies that have been developing automated driving over the past 5 or 6 years, most of especially the upstarts that aren't traditional OEMs, have been working with either Toyota or Lexus hybrid vehicles or Ford or Lincoln hybrid vehicles, because in both cases those vehicles are fairly readily available. They've got high voltage electrical systems. They're well understood, and it's fairly easy to tap into them to get the power that you need from those vehicles.
All right, thank you, Sam. Another question here asks, why would fuel cells be any more practical for AVs than they are today for commercial vehicles? Or excuse me, for conventional vehicles?
Yeah, so as I mentioned, today, in California, I think there's about 39 or 40 hydrogen filling stations, which for a state the size of California, not very much, especially with the number of vehicles we have here. Regular consumers expect to have, access to whatever fueling infrastructure or energy infrastructure they need for the vehicle wherever they want to drive. And one of the things that's limited the deployment of fuel cell vehicles today is that limited infrastructure. If you want to drive, from Los Angeles to Las Vegas in a fuel cell vehicle, that's going to be a problem, because you're not going to be able to get there and back without having another hydrogen station somewhere. But the vehicles that we're talking about, because most of the highly automated vehicles are going to be deployed in geographically limited areas, which could be a place like Los Angeles, or it could be San Francisco, or the Phoenix area, or Miami, or Singapore. Now, because those vehicles are going to be operating within a known geographic area, and they're part of a fleet, you can deploy a relatively smaller number of hydrogen filling stations to support that fleet, and those vehicles can use those as needed, because they're never going to drive much beyond the city limits of that location. And so it all that more limited infrastructure, fueling infrastructure, can support a large fleet that's limited geographically.
All right, thank you, Sam. Another question here asks, what level of electrification is required for an automated vehicle, and can a mild hybrid suffice?
Yeah, actually, a mild hybrid can suffice. You said right now for the development vehicles, which are typically using, computers that are not really purpose designed for this. Often they're, if you open up the trunk of one of these vehicles or the cargo area of one of these vehicles, you'll find, essentially a server rack sitting in the back, with some GPU cards and CPU cards. And those are consuming more power than you would in a production application. And also the current generation of sensors, especially the LiDAR sensors, are using more power. So those systems can be consuming up to 3 to 4 kilowatts of power. As we get towards more production intense systems with purpose designed compute platforms and sensors, that power demand is going to drop to probably somewhere between 1 and 2 kilowatts. And with a 48 volt electrical system, you have about 10 kilowatts of power, 10 to 12 kilowatts of power to work with most of the current systems on the vehicle, still operating within that roughly 2 kilowatt range. A 48 volt mild hybrid would very easily have plenty of power to provide for an autonomous driving system.
All right, thank you, Sam. Another question here for you asks, what are the expectations for what would normally be the aftermarket service industries and or the pre-owned automotive markets? How will they have to adapt?
Well, I'll address the second part of that first, the pre-owned part. Most likely, because most of these are going to be in fleet service, what we will probably see is most of these will never really go into the used car market, as we see today. They will probably, for the life of the vehicle, they'll probably remain, in the service of a fleet. And so that's not really an issue. And one of the things that, companies are starting to look at is as they start to develop purpose-designed vehicles for these applications, they're looking at the architecture of the vehicle. So today, we have vehicles that are designed to operate a minimum of 10 years, and they often last 15, 20, 30 years on the road. It's not unusual to see 30-year-old cars on the road in the United States today. And because of the relatively low utilization of those vehicles, that can happen. As you go to these high utilization vehicles like taxis, then the use case, or the wear pattern changes a lot, and so we're looking at having a vehicle architecture where perhaps the central core of the vehicle, the structure of the vehicle, may be something that's designed to last 10, 15, 20 years. Think of it like a bus, like a transit bus, where a transit bus chassis, will run for maybe 12 years, I think is the typical use cycle for those vehicles. Something like that. And then other components of the vehicle, things like the drive system, the batteries, and sensors and the communication systems can be designed for upgradability. It can be more modular. And so that, now for the service part of that, you're looking at refurbishment, rehab, upgradability of the vehicle. And because they're electric, some of the current service demands of those vehicles start to fall away. Obviously they don't need oil changes, but they still need, other service demands. The vehicles need to be cleaned if you've got people getting in and out of them all the time. Things like the interior of the vehicle, the materials that are used are going to be changed. You may be replacing seats, every couple of years in these vehicles or every few years, like they do in airliners. So the pattern of what parts are being replaced and who and how they're being replaced can change quite a bit. And if we're talking about, for example, automakers that are running their own fleet, like say GM Cruise has talked about, and what others are likely to do, for those companies that operate their own mobility services, they will likely end up partnering with perhaps their dealer networks. Because the dealer networks already have that service infrastructure in place, so they can leverage their dealers to provide, things like some of the cleaning and refurbishment services, and maybe even charging. That real estate that dealers have could also be the locations for charging stations or for battery swap stations. For companies like Waymo or Zoox, that want to operate their own fleets but that aren't currently manufacturers. Waymo's done over the last couple of years. They've done deals with Avis and AutoNation to provide servicing for their vehicle fleets. So there's potential for companies that are already in the business of maintaining and servicing vehicles to get new business with some of these mobility service providers to manage and maintain their fleets of vehicles. Hopefully I think I answered everything that was in the question there. But
yeah, I think you got it all. Another question for you, Sam, here. How will large fleets of electric vehicles impact the grid?
If we were to just throw out vehicles like we have, of the type that we have today, like for example, the Chevy Bolt fleet that GM Cruise operates in San Francisco right now, their test fleet, and we just continue, with kind of the same model that we have today, that could be a real problem, because there will definitely be more load on the grid if you have a large fleet of EVs that are being DC fast charged all the time within a small geographic area. That's why, I suggest that, options like battery swapping, where you can do slower charging, and then also tying that in, and even with existing vehicles, adapted vehicles like the Bolt, if you deployed them with bidirectional charging and, made arrangements to do vehicle-to-grid integration with those vehicles, because of the fluctuations in demand for some of the services over the course of the day, if you had an arrangement with the utility to perhaps park some of those vehicles at particularly high, peak periods of electrical demand, and had some revenue sharing arrangement with the utilities, that could offset the downtime that those vehicles have. So whereas normally if you're just taking the vehicles offline to charge them, to DC fast charge them, you're not generating any revenue. But if those vehicles, while they're being charged, they could be perhaps charged at a slower rate, or just parked when there's less demand for the use case, for the use, they could provide a grid buffer, so it could help stabilize the grid. So there's opportunities to actually improve the reliability of the grid depending on how you deploy this.
All right, thank you, Sam. Another question here asks, is there any industrial research going to charge EV batteries over the air in the interest of controlling utilities charges for AVs?
So you're talking about wireless charging of the batteries. There's certainly research going on, and some deployments of wireless battery charging. There's some companies there's a couple of companies that are doing that have wireless systems in place, like 200 kilowatt wireless charging systems for transit buses, and there's some pilot applications of that in a few locations, particularly in Europe. In general, wireless charging, there are some issues with it, particularly for higher power charging. One of the issues, for a place where it could work is for applications like what May Mobility is doing. I showed May in the presentation. May operates their low-speed shuttle fleet on a fixed route service, so it's kind of like a microtransit service. Like tiny 6-passenger buses, if you will. And when you're operating in that kind of application on a fixed route, and you know where the vehicle is going to be all the time, and there are certain stops along the way, that's someplace where you could actually deploy wireless charging, over-the-air charging for those vehicles, because you know where they're going to be. When you shift to a more point-to-point, or free-floating type of application, like a ride-hailing type of application, or cargo delivery, and you don't necessarily know where those vehicles are going to be at any given time of the day, then the wireless charging becomes more problematic to try to implement that. Just the logistics of it are more problematic. So I think where we'll see the greatest potential for wireless charging will be in those fixed route type of applications.
All right, thank you, Sam. Another question asks, what do you think about restricting the deployment of AV EVs to good climate locations due to their battery performance hit in cold weather, and the autonomous sensors difficulty with snow and adverse weather, etc.
Yeah, I mean, certainly, cold weather conditions are a problem for EV batteries, and then when you stack AV on top of that, it just makes it worse. That part, I think, is less of an issue. I mean, it may cause some operational challenges just in terms of you have to either charge more frequently or do battery swaps more frequently. But I think that's a relatively straightforward one to overcome. The geographic restrictions, I think, is more of an issue for the AV stack because just in terms of trying to get the system to operate in adverse weather conditions, to operate reliably and safely in adverse weather conditions. There are issues with sensors being able to see through snow or heavy rain. Certainly cameras struggle with those kinds of environments, but even LiDAR can have issues with that. There are certain types of LiDAR, like the Doppler LiDAR being developed by a company called Blackmore, that actually has the potential to be able to filter out raindrops and snowflakes. Other LiDAR companies are also working on similar approaches to maybe have reduced visibility, just as we as humans do in those conditions, but still be able to operate. So that's one of the, but that sort of thing is probably the biggest challenge from a technology standpoint, is actually being able to sense the environment reliably in those adverse weather conditions, and that I think will be more of a problem than the electrification part of it.
All right, thank you, Sam. Another question here asks, it's related to insurance. It's asking, how are insurance companies handling this situation with driverless cars, and will the insurance be expensive?
That's a very good question, and probably the best example right now is Tesla. A lot of insurance companies do charge significantly more for insurance on Tesla vehicles, in part because of concerns of autopilot, but also because of the higher cost of repair for those vehicles. But in general, there are some concerns with repair costs on both with automation and also ADAS, driver assistance systems, and that could be a real issue. On the other hand, automated vehicles, when used in automated mode, if the system's working correctly, should be less likely to crash. So the frequency of crashes will be less. The cost of repairs when a crash does happen, maybe if a human driver runs into an AV, or if the AV system fails, the repair cost would be higher, but the frequency should go down. Insurance companies are currently trying to understand, what the issues are going to be, how they're going to address this. So there's still a lot of unknowns with this going forward, but hopefully, just the reduced frequency of crashes should help to bring down overall costs. And ultimately, it may impact and fundamentally change the car insurance business. If we get to the point where vehicle crashes are reduced by 50, 60, 80%.
All right, thank you, Sam. Another question here regards taxi fleets and asks, our taxi fleets are normally Prius 50 mile per gallon vehicles. So does an EV pay for itself relative to a PHEV? And what is the dollar to gallon to dollar to kilowatt spread have to be to overcome the first price difference?
Ooh, that's a good one. I don't have all the numbers at my fingertips right now, but that's certainly something that if you want to reach out to me later, we can take a look at that. But in general, there are a lot of Priuses in use in taxi fleets, but they are not by any means universal. Depending on where you go. Certainly in California, there's a lot of them. Other areas, fewer. New York, you've got a lot of Nissan NV200s. The cost differential, operating cost differential, versus a Prius is going to be a challenge because as you get to higher and higher fuel economy, the amount of fuel that you use the incremental reduction in cost for every additional mile per gallon goes down. And if you're going from a 50 mile per gallon Prius to an EV that's getting maybe equivalent of about 80 to 100 mpge, or actually probably less if it's automated, that cost differential is going to be a lot less. Or at least the energy savings are a lot less. Electricity is still a lot cheaper than gasoline in most places. So there probably will still be some savings, significant savings. But of course, you've also got other new costs that are associated with deploying this kind of technology. So, the expectation, the hope, the goal is to reduce the costs of providing, like for ride-hailing services today, it averages somewhere in the neighborhood of $2.50 a mile. The goal is to get it down to under under $1 per mile for automated ride-hailing services, but it's going to take a while to get there, both because of the cost of the technology and the service required for those vehicles, the maintenance.
All right, thank you, Sam. We have another question here talking about the charging situation. Why can't cars or vehicles generate energy to charge their batteries while driving? So say you have two batteries, one is charging while the other is being used for the power of the vehicle.
That's the old perpetual motion question. Yeah, I mean, certainly, hybrid vehicles and battery electric vehicles do in fact generate some energy while they're driving. When they're decelerating, we can recapture a significant amount of the kinetic energy and put it back in the battery, and that's why those vehicles are so much more overall efficient than a traditional gas or diesel vehicle. But if you're, ultimately, there's going to be losses associated with, both with the charging system. None of these processes, even though you can recapture energy in an electrified vehicle, none of the processes are 100% efficient. There are always losses. And then, if you were to talk about adding a second battery to the vehicle, now you've added significant amount of extra mass. Batteries are very bulky, so there's packaging space, there's mass associated with that. Now it takes more energy to drive that vehicle. So you're never really going to recover all of that energy. So there's always going to be some significant loss along the way.
All right, thank you, Sam. Well, that looks like all the questions that we have for today. I'd like to thank Sam Abu Al-Samid. Design News appreciates your time and expertise on today's topic. Great job on the Q&A and the presentation. We'd also like to thank our sponsor, Highland Molex, and also IPEX, and Protolabs, and Siemens, as well as everyone in the audience, and we appreciate your attention and participation. Within the next 24 hours, you'll receive a personalized follow-up email with details and a link to today's presentation on demand. And please feel free to invite your colleagues and peers who may not have been available to listen to today's event. Once again, if for some reason we did not get to your particular question today, someone will get back to you after the program is over. And this webinar is copyright 2019 by Informa. The presentation materials are owned by our Copyright by Design News, Highland Molex, IPEX, Protolabs, and Siemens, and the individual speaker is solely responsible for his content and opinions. On behalf of our guest, Sam Abu Al-Samid, I'm Chris Keach. Once again, we'd like to thank you for joining us, and we hope you have a great day.